Hi, this is an example problem from Chapter 9 that uses the conservation of mechanical energy for rolling motion. There's a video that actually shows a demonstration of this in the introduction to the week 10 if you want to watch that. Pause for a moment and read the problem. All right, so we've got two different cylinders that have the same radius and the same mass that are going to race down an incline. And we're going to go ahead and see which one has the greater translational speed v at the end. That's the one that wins. It's going faster at the end. It got down quicker. We can actually analyze both of these in the same method to begin with. We're going to use energy, and the conservation of mechanical energy, we're going to use it just like we did before. The total mechanical energy is the sum of the kinetic plus the potential. In this case, we've got two types of kinetic. We've got the translational kind, 1/2 mv squared, but we've also got rotational kinetic energy, which is 1/2 I omega squared. And of course, we've also got the gravitational potential energy. So with the conservation of mechanical energy, we know that we've got at the top, the initial mechanical energy has a certain value, and it's going to be the same as the total mechanical energy at the bottom, right? So we want to identify this is initial here where we start at the top, and this is final here where we end at the bottom. And we're going to be looking at kinetic energy and potential energy. Let's go ahead and draw a little axis here to measure the height, which is involved with potential energy. So down at the bottom here, let's call this our reference point H final here at the bottom is equal to 0. And over here at the top, we're measuring from the center of these things, H initial here, we're told 25 centimeters. Let me convert that to SI units, meters. And we're also going to want to know for these objects, right? It doesn't matter whether I'm doing hollow or solid cylinder, but in general, in the beginning, we're going to need to know what is the initial translational speed. Well, it's 0 for both because they start from rest. And then what we're trying to figure out at the end, what is the final translational speed? And also, what is the initial rotational speed or the angular speed? Well, they also start from rest, so it's 0. And what is the final angular speed down here at the bottom, right? We don't know what that is either. So using the conservation mechanical energy, right, we're going to add up your kinetic energy of translation plus your kinetic energy in the beginning, rotation in the beginning, plus your potential energy in the beginning, and that's going to be equal to those same things at the bottom. And we know that we have some equations for these, right? So the standard kinetic energy translational, 1/2 mv squared, the rotational variety, 1/2 I omega squared, and the potential energy, of course, for gravity, mgh. Now we can actually relate these two values here, the translational speed and the angular speed, by using the rolling condition, right? So the rolling condition says the translational speed is equal to the radius of the rolling object times its angular speed. If we solve for omega from this equation, we're going to see that omega is equal to v divided by r. And I want to substitute that in here. So I'm going to have 1/2 I, what's omega? Omega is equal to v over, use a capital R because that's what's given here. We're going to square that. And if we look at that, we're going to end up with 1/2 I v squared over r squared. So now we've got equations only in terms of the translational speed v. Let's go ahead and see what we can cancel out. So in the beginning at the top, we know that the kinetic energy is 0 for both types. And at the end, the potential energy, because of being back to 0, is 0. And so this is what we have at the moment. We've got potential energy initial, mass. So we're using big letters here. So capital M times G times h0, and then that's equal to your kinetic energy translational final, which is 1/2 capital M V final squared. For the rotational kinetic energy, it's 1/2, and we've got in this case I V squared divided by R squared. And this is final velocity. Now we're trying to solve for V final, so let's go ahead and rearrange this and algebraically solve for it. First thing I'm going to do is just reverse the two sides of the equation to get V final on the left-hand side. Now I want to factor out V final squared on this side here. I'm going to be left with an M divided by 2 plus an I divided by 2 R squared is equal to mg h0. So we're almost there now, and we just need to go ahead and divide both sides by the term in parentheses and then take the square root. So that's going to be an mg h0 all divided by m over 2 plus I over 2r squared, and then we'll take the square root of both sides. Remember that the speed is always positive. And there's our equation for the final speed. Now, since these two objects both have the same mass and the same radius, the only thing different for the two is the moment of inertia. And so we can use the same equation for each. We just got to pick the right moment of inertia for the two different ones. And so in part A, we're going to solve for the final speed of the solid wood cylinder. And for part B, we're going to solve for this final speed of the hollow metal cylinder. Which one do you think is going to have the largest moment of inertia? Which one do you think is going to be the winner? Well, you can see that it's the solid one, right? Solid one has the smallest moment of inertia. It has less resistance to rotation, therefore it wins. And let's show that here by plugging in the values. So let's look up the moment of inertia for these two objects. For the solid cylinder, it's 1/2 mr squared. And for the cylindrical shell, it's twice as much. It's mr squared. A is the solid cylinder, so we've got here I 1/2 mr squared, and for B, cylindrical shell, it's going to be mr squared. So we need to go ahead and just plug in the numbers for these two situations. So this is going to be an mgh0, 0.5 kilogram, times g, 9.8 meters per second squared, times h initial, 0.25 meters, all divided by the mass, capital M, 0.5 kilograms, divided by 2, plus, now I'll leave this I for a moment here, and I'm going to divide by 2 times R, which in this case is equal to 6 centimeters, that's 0.06 meters. We got to square that. And so that's the same equation for both. We're just going to be plugging in different values for I in these two cases. So let me just go ahead and write down the values for I here. So this is going to be 1/2 m 0.5 kilograms times the radius of these objects, 0.06 meters squared. And for the one below, it's going to be the same thing, but it's going to just be without the 1/2. And we need to plug those values in for I and then calculate V in both cases. I'm going to go ahead and just put those numbers in and see what we get. All right, so for part A, when we take this number here and plug it right in there, we end up with the value for V final, which is equal to 1.81 meters per second. Whereas when we take the I for the part B hollow metal cylinder, the larger value, and plug it into that same equation, we end up getting a V final here, a smaller value equal to 1.57 meters per second. So when we look at these two values, we compare them, we can see that the one that reaches the bottom with the higher speed, the solid disc of wood, that one is the winner in the race. One last thing we might want to check. Did the units come out as we expect from that big equation there? Well, in the numerator, what do we have? Let's see, kilograms, meters squared, divided by seconds squared, right? And in the denominator, we've basically got this term's got kilograms. The other term, I, is kilograms meters squared, so it'll cancel. It's got to be kilograms as well. So we're basically having kilograms on the bottom there. Cancel those, and then we're taking the square root, right? That's going to end up with meters per second as we expect. So everything looks good here, and again, the one that wins is the one that has the least resistance to rotational motion, the solid wooden cylinder, because it has more of its mass closer to the central axis, right through the center of the cylinder.